We are surrounded by millions of stars and planets, each hiding its own secrets and amazing sights. But beyond their beauty, there's a scarier side to these celestial bodies. In the dark depths of our universe, there are planets so frightening and strange, they make us rethink what it means to be a planet. Imagine planets where the rain is made of glass, falling sideways at super-fast speeds, or worlds covered in constant darkness, where the light from their star never reaches the ground. There are giant gas planets where the air pressure would crush you long before you could even land on them, and rocky planets with seas of lava always moving under a burning sky. These aren't the peaceful blue spheres with white clouds or the red neighbors that have caught our attention for so long. These are places of extreme conditions, where nature's rules create environments so deadly they seem like they're out of our scariest dreams. Join us on this journey as we explore the most terrifying and scary planets in our universe. TRES-2 b, often hailed as one of the darkest exoplanets ever discovered, serves as a fascinating subject for anyone intrigued by the mysteries of our cosmos. Located about 750 light-years away from Earth in the constellation Draco, TRES-2 b was first detected in 2006 through the Transatlantic Exoplanet Survey, a project aiming to find planets outside our solar system by observing how stars dim when a planet passes in front of them, a method known as the transit method. This celestial body orbits its star every 2.5 days, a short period that hints at its close proximity to the star, approximately 3 million miles away, which is much closer than Mercury is to our Sun. What sets TRES-2 b apart from other exoplanets is its astonishing lack of reflectivity. Scientists have determined that it reflects less than 1% of the light that hits it, making it darker than coal or any other planet or moon in our solar system. This characteristic is primarily due to its atmosphere, which contains light-absorbing chemicals like vaporized sodium and potassium and the absence of clouds. This absorption of light contributes to its extremely high surface temperature, soaring above 1800 degrees Fahrenheit, making it one of the hottest planets we know of. Moreover, despite its darkness, TRES-2 b has a unique feature that prevents it from being completely invisible to observers. The planet possesses a faint red glow, a result of the intense heat causing it to emit light, much like the embers of a fire. This glow adds a mysterious aura to TRES-2 b, enhancing its allure among astronomers and casual stargazers alike. The extreme proximity of TRES-2 b to its host star results in a phenomenon known as tidal locking. This means that one side of the planet always faces the star, receiving perpetual daylight, while the other side remains in endless night. This permanent day-night divide creates a dramatic contrast in temperatures across the planet, potentially leading to fierce winds and complex weather patterns that defy our Earth-bound meteorological knowledge. The atmospheric conditions of TRES-2 b are no less fascinating. The presence of vaporized metals such as sodium and potassium, along with the absence of reflective cloud cover, suggests an atmosphere that is both alien and hostile by earthly standards. Researchers speculate that the planet could also host exotic forms of clouds made from compounds utterly foreign to us, possibly contributing to its dark appearance. The detection of such elements and compounds in the atmosphere provides crucial clues to understanding the chemical processes that take place on TRES-2 b, offering insights into the planet's formation, evolution, and current state. The study of TRES-2 b also plays a pivotal role in the broader context of exoplanet research. By comparing TRES-2 b with other exoplanets, scientists can explore the diversity of planetary systems in our galaxy. For instance, the extreme characteristics of TRES-2 b highlight the vast range of possible planet types, from those with thick, dense atmospheres to others that are rocky, barren, or even water worlds. These comparisons are essential for developing a comprehensive understanding of planet formation and the potential for life in the universe. TRES-2 b's unique features make it a prime candidate for future observations with more advanced telescopes and instruments. The James Webb Space Telescope, along with other ground-based observatories, are poised to offer unprecedented views of exoplanets like TRES 2b. These future observations will likely provide more detailed information about the planet's atmosphere, surface conditions, and perhaps even clues to its geological activity. Continuing our exploration of the cosmos, we journey to 55 Cancri E, an exoplanet that captivates the imagination with its extraordinary characteristics. Situated approximately 40 light-years away in the constellation Cancer, 55 Cancri E is a world of extremes, a so-called super-Earth that is about twice the size of our planet and 8 times its mass. This intriguing exoplanet orbits its host star, 55 Cancri A, at such a close distance that a year there lasts a mere 18 hours, a stark contrast to our 365-day orbit around the Sun. What sets 55 Cancri E apart in the pantheon of exoplanets is not just its size or its incredibly short orbital period, but its potential surface conditions, which have led to speculative titles like Diamond Planet. Scientists theorize that the intense pressure within 55 Cancri E could transform carbon into diamond, creating a world that quite literally sparkles with these precious gems. This hypothesis stems from observations and models suggesting the planet's composition is rich in carbon alongside other elements. While the romantic notion of a diamond planet captures the imagination, it's important to remember that this is a hypothesis, one of many theories that researchers are eager to test with more advanced observational tools. The temperature on 55 Cancri E is another aspect that fascinates scientists and laypeople alike. With surface temperatures soaring to over 4,000 degrees Fahrenheit, this planet is far from hospitable to life as we know it. The extreme heat, a result of its proximity to its star, ensures that any atmosphere present is unlike anything in our solar system, possibly consisting of heavy gases in a supercritical fluid state, a state that blurs the line between gases and liquids. As we delve further into the enigma that is 55 Cancri E, it's clear this planet holds a trove of secrets that challenge our understanding of planetary systems. Its close orbit around its host star, a mere 1.5 million miles away, places it in a category of exoplanets known as ultra-short-period planets. This proximity leads to one of the most intriguing aspects of 55 Cancri E. The tidal forces between the planet and its star are so intense that the planet is likely tidally locked. This means one side of the planet constantly faces the star, basking in perpetual daylight, while the other side is shrouded in eternal darkness. The stark contrast between the day side and night side of 55 Cancri E has profound implications for its climate and atmospheric dynamics. Scientists speculate that the temperature difference could drive supersonic winds, transporting heat from the blistering day side to the cooler night side. This extreme weather system could result in a complex and dynamic atmosphere, unlike anything observed in our own solar system. Adding to the mystery of 55 Cancri E is the composition of its atmosphere. Early observations suggested the presence of water vapor, but more recent studies hint at a hydrogen-rich atmosphere, with layers possibly containing hydrogen cyanide, a marker of carbon-rich environments. Such findings further fuel the speculation that 55 Cancri E could indeed be a diamond planet, with a carbon-heavy interior that might turn into diamond under the planet's extreme pressure and temperature conditions. The potential for 55 Cancri E to host an atmosphere rich in carbon compounds not only intrigues scientists, but also stirs the imagination about what other kinds of worlds could exist in the vast expanses of our galaxy. The planet's study is at the frontier of exoplanet research, pushing the limits of current observational technologies and theories of planet formation and composition. Embarking further into these mysterious planets, we encounter Gliese 581c. Discovered in 2007, Gliese 581c orbits the red dwarf star Gliese 581, situated roughly 20 light-years away in the constellation Libra. This exoplanet is particularly noteworthy for its position within its star's habitable zone, the region where conditions might be right for liquid water to exist, a crucial ingredient for life as we know it. Gliese 581c is about 1.5 times the size of Earth, making it a super-Earth, and has a mass around 5.5 times that of our planet. These dimensions suggest that Gliese 581c has a significantly higher gravity than Earth, which would have profound effects on the planet's atmosphere and potentially on any water or life forms present. The planet completes an orbit around its host star in just under 13 days, a fact that points to its close proximity to Gliese 581 and raises intriguing questions about its climate and atmospheric conditions. One of the most captivating aspects of Gliese 581c is the possibility that it may harbor liquid water, a hypothesis that hinges on the planet's temperature and atmospheric pressure. If conditions are just right, Gliese 581c could have oceans, rivers, or lakes of water, environments that on Earth are teeming with life. However, scientists also caution that the planet's close orbit could mean it's tidally locked, with one side perpetually facing its star and the other in constant darkness. This could result in extreme temperature variations across the planet, with one side possibly too hot and the other too cold for liquid water to persist. As we delve deeper into the mysteries surrounding Gliese 581c, we uncover layers of complexity that challenge and expand our understanding of habitable worlds. The intriguing prospect of this planet being within its star's habitable zone does more than just spark the imagination. It drives forward the scientific quest to understand the conditions under which planets can sustain life. The study of Gliese 581c, along with its sibling planets in the Gliese 581 system, offers a rich tapestry for understanding the diversity of planetary environments. The concept of a tidally locked planet, such as Gliese 581c might be, introduces fascinating scenarios for climate and weather patterns. On such a world, the stark contrast between the perpetual day and eternal night sides could create powerful atmospheric dynamics. Scientists speculate that if the planet has an atmosphere, it might circulate heat from the day side to the night side, potentially allowing for a more even temperature distribution than one might expect. This could create a twilight zone, a region where temperatures might be conducive to liquid water and, conceivably, life. The challenges of exploring a planet like Gliese 581c are immense, given its distance from Earth and the current limits of our technology. However, projects and missions in development aim to launch telescopes that can observe exoplanets directly, analyzing their atmospheres for signs of water vapor, oxygen, methane, and other gases that might indicate the presence of biological processes. Such observations could provide indirect evidence of life, or at the very least, of environments where life as we know it could exist. Furthermore, the study of Gliese 581c contributes to our understanding of red dwarf stars and their planetary systems. Red dwarfs are the most common type of star in the Milky Way, and their long lifespans provide a stable environment for potentially habitable planets. However, their propensity for powerful flares could pose a risk to the atmospheres of closely orbiting planets, stripping away the very conditions necessary for life. Understanding how planets like Gliese 581c withstand their stellar environments is crucial for assessing the habitability of planets around red dwarfs. Nestled within the cosmic neighborhood, Proxima Centauri B presents a tantalizing glimpse into the potential for life beyond Earth. Orbiting Proxima Centauri, the closest known star to the Sun at a mere 4.24 light-years away, this exoplanet captures the imagination and curiosity of scientists and space enthusiasts alike. Discovered in 2016, Proxima Centauri B is situated in the habitable zone of its star, where temperatures could allow for liquid water to exist on its surface under the right atmospheric conditions. This intriguing world is approximately 1.3 times the mass of Earth, suggesting it is a rocky planet much like our own. The close proximity to its star means Proxima Centauri B completes an orbit in just 11.2 Earth days, presenting a scenario where the planet could be tidally locked. This would result in one side of the planet always facing the star, basking in perpetual daylight, while the other side languishes in endless night. The implications for climate, weather, and potential habitability are profound, sparking discussions and studies aimed at understanding this unique environment. Despite the excitement surrounding Proxima Centauri B, the red dwarf star it orbits is known for its temperamental nature, often emitting powerful flares. These stellar outbursts could pose significant challenges to the potential for life, possibly stripping away the atmosphere or subjecting the surface to high levels of radiation. Yet the possibility remains that, under the right conditions, Proxima Centauri B could support an atmosphere that protects it from these harsh stellar winds, preserving the potential for habitability. Given its proximity to its host star, Proxima Centauri B is subjected to intense stellar radiation, much more than Earth receives from the Sun. This factor plays a crucial role in determining the planet's atmosphere and surface conditions. If Proxima Centauri B has a strong magnetic field, similar to Earth's, it could shield the planet from some of these harmful radiations, making it a more hospitable environment than initially thought. The existence of water in any form on its surface would be a groundbreaking discovery, significantly boosting the potential for life. The intriguing aspect of Proxima Centauri B's orbit, potentially being tidally locked, raises questions about the climate dynamics on such planets. The concept of a permanent day side and a permanent night side suggests extreme weather conditions, with possible implications for atmospheric circulation patterns that could distribute heat around the planet. Scientists hypothesize that if Proxima Centauri B has an atmosphere, it might have a temperate zone at the boundary between the light and dark sides, where conditions could be conducive to liquid water and, by extension, life. The ongoing and future missions aimed at exploring Proxima Centauri B are equipped with sophisticated instruments designed to detect the faintest signals of an atmosphere and analyze its composition. Spectroscopy, a method used to identify the chemical makeup of a planet's atmosphere by studying light from the star as it passes through, could reveal the presence of molecules like oxygen, carbon dioxide, and methane, all of which could hint at biological processes. The prospect of sending a probe to Proxima Centauri B, although decades away, sparks the imagination. Such a mission would provide direct observations and data, offering insights into the planet's geology, atmospheric conditions, and potential biosignatures. Current initiatives, like the Breakthrough Starshot project, aim to develop the technology necessary to send small, light-powered spacecraft to the Alpha Centauri system, of which Proxima Centauri is a part, marking a monumental step in interstellar exploration. Venturing further into the cosmos introduces us to Pimen C, a compelling exoplanet that holds its own unique place within the vast tapestry of known celestial bodies. Discovered orbiting the star Pimen C, located some 60 light-years away in the constellation Mensa, this planet is part of a growing list of worlds that challenge and expand our understanding of planetary systems beyond our own. Pimen C is particularly notable for being a super-Earth, a type of exoplanet with a mass higher than Earth's but substantially lower than that of the ice giants Uranus and Neptune. Its discovery, announced in 2018 through data from NASA's Transiting Exoplanet Survey satellite, marked a significant achievement in the search for exoplanets. Pimen C has a mass around 4.82 times that of Earth and completes an orbit around its star every 6.27 days, indicating a close proximity to its host star, much closer than Mercury is to the Sun. What makes Pimen C fascinating is not just its size or orbit, but its position within a system that also hosts a gas giant, Pimen B, discovered in 2001. This setup provides a rich field for studying the dynamics of multi-planet systems, especially with such contrasting types of planets, a super-Earth and a gas giant, cohabiting around the same star. The differences in their compositions, orbits, and potential atmospheres offer a wealth of data for scientists trying to understand the variety of planetary environments that exist in our galaxy. Despite its proximity to its host star, the question of Pimen C's habitability or its potential to host an atmosphere remains open. Its close orbit suggests it could be subjected to intense stellar radiation, possibly affecting any atmosphere it might have. However, the detailed study of its atmospheric composition, which could reveal the presence of gases like water vapor or carbon dioxide, has yet to be conducted. These studies are crucial for assessing not just the conditions on Pimen C, but also the potential for life on planets that share its characteristics. The story of FAL B is as mysterious as it is fascinating. Initially discovered in 2008 through the keen eye of the Hubble Space Telescope, it was celebrated as one of the first exoplanets, planets outside our solar system, directly imaged, offering a glimpse into the methods of detecting and studying distant worlds. However, the planet's existence soon became a matter of debate. Unlike the rocky or gas giants found in our solar system, FAL B did not emit any infrared radiation, an oddity that puzzled scientists. Infrared radiation typically indicates a planet's heat, which can be used to infer its size and composition. The plot thickened when further observations failed to detect the planet consistently. It seemed to vanish and reappear in different datasets, behaving more like a ghostly apparition than a solid celestial body. This led to a sensational turn in 2012 when researchers proposed that FAL Hobe might not be a planet at all. Instead, it could be a vast cloud of dust resulting from a colossal collision between two icy bodies, remnants orbiting FAL Hobe. This hypothesis painted a picture of a cosmic demolition derby, with FAL B as the fleeting evidence of a dramatic event. But the story does not end there. The debate continued to evolve with more observations and studies. Some astronomers hold on to the planet hypothesis, suggesting that FAL B might be a planet shrouded in a huge cloud of dust, perhaps from a massive ring system or the aftermath of an impact, which could explain the unusual observations. This theory keeps the door open for FAL Hobe's planetary status, suggesting it might be a world unlike any we've encountered. The journey of discovery surrounding this distant world showcases the leaps in astronomical techniques and the persistent curiosity that drives the scientific community forward. After its initial detection, the narrative of FAL B became a catalyst for debate and innovation, encouraging astronomers to refine their methods of observing and interpreting data from the far reaches of space. Advancements in telescopic technology and imaging techniques have been at the forefront of this quest. The Hubble Space Telescope, with its unparalleled view of the universe, free from the distortions of Earth's atmosphere, played a pivotal role in the story of FAL B. Yet, the intrigue of FAL B pushed scientists to look beyond conventional methods. The application of dynamic imaging and the pursuit of infrared signatures using other space and ground-based telescopes added layers of complexity to the investigation, illustrating the multifaceted approach required to study such elusive targets. The scientific interest in FAL B also highlights a broader theme in the field of astronomy: the search for exoplanets and the conditions that might support life. Each discovery, each anomaly encountered in the vastness of space brings us closer to understanding our place in the universe. The peculiar case of FAL B, with its disputed nature and the mysteries surrounding its existence, serves as a bridge to ponder more profound questions about planet formation, the diversity of planetary systems, and the potential for habitable worlds beyond our solar system. Moreover, FAL B's story is a testament to the dynamic nature of the universe. If indeed the result of a colossal impact, it reminds us of the constant changes occurring in cosmic scales of time and space, shaping and reshaping the architecture of galaxies. The potential for new worlds to be born from the debris of such cataclysmic events, or for existing planets to be cloaked in dust clouds, enriches our understanding of planetary evolution and survival in the harsh environment of space. Deep within the universe, there exists a planet that seems almost out of place in the cosmic narrative due to its sheer age. This character is not a mythical figure but a star, known affectionately as Methuselah, or more formally as HD 140283. Methuselah's story captivates not just because of its age, but because it challenges our understanding of the cosmos, offering a paradox that has puzzled astronomers for years. Methuselah is intriguing because its age, estimated to be around 14.5 billion years, appears to defy logic. This estimation puts it at nearly the same age as the universe itself, which, according to current cosmological models based on the Big Bang theory, is about 13.8 billion years old. The apparent conundrum of a star older than the universe prompts a deeper dive into the methods used to determine stellar ages and the uncertainties inherent in these measurements. The age of Methuselah was estimated using a technique that involves measuring its composition and its movement. Stars, much like people, change as they age, and by understanding a star's composition, particularly its metallicity, or the abundance of elements heavier than helium, astronomers can infer its age. Methuselah has an unusually low metallicity, indicating it formed when the universe was very young and contained few elements beyond hydrogen and helium. The star's speed and trajectory also offer clues to its ancient origin, suggesting it belongs to the halo of the Milky Way, a population of stars that envelops the galaxy and includes some of its oldest members. The apparent age discrepancy of Methuselah has led scientists to refine their methods and question their assumptions. It has sparked discussions about the precision of age-dating techniques, the interpretation of data, and even the models of stellar evolution. This ongoing debate exemplifies the dynamic nature of science, where anomalies challenge established theories and drive the quest for greater understanding. In addressing the Methuselah paradox, researchers have considered various factors that might affect their age estimates, such as the star's initial composition and the impact of its environment. Adjustments to the models of stellar evolution and more precise measurements of the star's properties have narrowed the age gap, suggesting Methuselah may be slightly younger than initially thought, but still remarkably ancient. WASP-12 b, a distant and exotic world far beyond our solar system, presents a stark contrast to the celestial bodies we've previously explored. This intriguing planet, discovered in 2008, orbits the star WASP-12, located approximately 600 light-years away in the constellation Auriga. What makes WASP-12 b stand out in the vast catalogue of exoplanets is its classification as a hot Jupiter, a type of gas giant that orbits very close to its host star, leading to extreme atmospheric conditions. With a mass almost 1.4 times that of Jupiter but an orbital period of just over a day, WASP-12 b's proximity to its star results in surface temperatures soaring above 2,200 degrees Celsius. This intense heat has profound effects on the planet's atmosphere and structure, causing it to assume an elongated shape rather than a perfect sphere. Scientists have observed that the high temperatures on WASP-12 b lead to the presence of heavy metals like iron and magnesium in its atmosphere, elements that in cooler gas giants would condense into clouds. Another remarkable feature of WASP-12 b is its tidal interactions with its host star. The gravitational forces at play are so strong that the planet is being gradually pulled closer, leading to a scenario where WASP-12 b may eventually be consumed by WASP-12. This grim fate is not immediate, but the process provides a fascinating glimpse into the life cycle of exoplanets and their stars. WASP-12 b also plays a crucial role in the study of planetary atmospheres. Its detection and analysis have been made possible through transit observations, where the planet passes in front of its host star from our perspective, allowing astronomers to study the starlight that filters through the planet's atmosphere. This method has revealed much about WASP-12 b's composition and behavior, offering insights into the chemistry of other hot Jupiters. WASP-12 b was discovered through the Wide-Angle Search for Planets (WASP) project, a ground-based effort designed to detect planets outside our solar system using the transit method. The transit method involves monitoring the brightness of stars over time and looking for periodic dimming, which indicates that a planet is passing in front of the star from the observer's perspective. This method is particularly effective for identifying planets that orbit close to their host stars, as these planets tend to transit more frequently and produce more noticeable changes in brightness. In the case of WASP-12b, astronomers observed a slight dip in the brightness of its host star, WASP-12, which occurs every 1.1 days, the period it takes for the planet to complete an orbit around its star. The regularity and depth of these dips in brightness provided clear evidence of a planet's presence and allowed scientists to calculate its size and orbital distance. Subsequent spectroscopic observations, which analyzed the star's light to detect the gravitational pull of the planet, confirmed the planet's mass and further details about its characteristics. The discovery of WASP-12b was significant because it added to the growing list of exoplanets that challenge our understanding of planet formation and behavior, particularly those in close orbits around their stars. It also underscored the efficacy of the transit method and ground-based telescopes in contributing to exoplanet science, a field that has rapidly expanded since the first exoplanets were confirmed in the 1990s. Discovered by the Kilodegree Extremely Little Telescope or Kelt survey, Kelt 9b orbits a star some 670 light-years away in the constellation Cygnus. This planet is not only remarkable for its sheer size, closely resembling that of Jupiter, but it's also distinguished by its extreme temperatures and the peculiar nature of its orbit around a blue A-type star, one of the hottest stars known to host a planet. Kelt 9. B's discovery unveiled a world where daytime temperatures soar above 4,300 degrees Celsius, about 7,800 degrees Fahrenheit, hotter than many stars and setting the record for the hottest exoplanet discovered to date. Such blistering temperatures are attributed to the planet's close proximity to its host star, Kelt 9, which it orbits every 1.5 days. This rapid orbit places Kelt 9b in a category of ultra-short period planets, experiencing conditions that are beyond the extremes found in our own solar system. The intense radiation from its host star has profound effects on the planet's atmosphere. Studies suggest that the ultraviolet light is so powerful it can split molecules apart, preventing the formation of many chemicals common in cooler planetary atmospheres and leading to a predominantly atomic composition. This has piqued the interest of astronomers, as it provides a unique laboratory for studying atmospheric chemistry under extreme conditions. Moreover, Kelt 9b's atmosphere contains ions, such as ionized iron and titanium, unusual for planetary atmospheres and indicative of the extreme heat that can ionize metals. The presence of these metals in gaseous form provides insights into the planet's atmospheric dynamics and the types of chemical reactions that can occur under such intense irradiation. As we further explore the mysterious nature of Kelt 9b, the planet's relationship with its host star takes center stage, revealing a dynamic and potentially catastrophic future. The extreme temperatures and rapid orbit of Kelt 9b are just the beginning of its story. The gravitational forces exerted by its host star, Kelt 9, are causing tidal interactions that have profound implications for the planet's structural integrity and long-term survival. These tidal forces are not only responsible for Kelt 9b's elongated shape, but also contribute to the gradual decay of its orbit. Over time, it is expected that Kelt 9b will spiral closer to its star, leading to increased heating and atmospheric loss. This process, known as orbital decay, could ultimately result in the planet being consumed by its star. Such a fate underscores the transient nature of some exoplanetary systems, offering a glimpse into their life cycle and evolution. The study of Kelt 9b also sheds light on the mechanisms of atmospheric escape. The intense heat and radiation from Kelt 9 are powerful enough to strip away the planet's atmosphere, atom by atom, into space. This atmospheric escape is observable as a tail of gas being blown off the planet, akin to a comet's tail, providing direct evidence of the harsh conditions that prevail. Furthermore, the peculiarities of Kelt 9b extend to its night side, which remains a subject of intrigue. Despite the extreme temperatures on its day side, the night side of the planet experiences significantly cooler, though still extremely high, temperatures. This discrepancy poses questions about the efficiency of heat distribution across the planet's atmosphere and the potential for complex atmospheric dynamics involving winds and jet streams. The exploration of Kelt 9b has broad implications for our understanding of exoplanetary atmospheres, particularly those orbiting close to their stars. It challenges astronomers to develop models that can accurately predict the behavior of planets under such extreme conditions, contributing to our broader understanding of planetary science. Continuing our journey in space, we encounter Kepler 10b, identified by the Kepler Space Telescope, which was tasked with discovering Earth-like planets in habitable zones. Kepler 10b orbits its star some 560 light-years away in the constellation Draco. This exoplanet holds the distinction of being one of the first rocky planets confirmed outside our solar system, providing a glimpse into the diverse planetary compositions that exist beyond our familiar celestial neighborhood. Kepler 10b is a world of extremes, with a mass 3.3 times that of Earth, yet it orbits its star at a distance more than 20 times closer than Mercury is to our Sun. This close proximity results in a year on Kepler 10b lasting just 0.84 Earth days, and contributes to surface temperatures that can exceed 1,300 degrees Celsius, about 2,372 degrees Fahrenheit. Far too hot to support life as we know it. The planet's surface is thought to be molten in some areas, with possibly oceans of lava, a testament to the intense heat generated by its star. The discovery of Kepler 10b was significant for several reasons. It was the first planet found by the Kepler mission to have both its size and mass measured, allowing scientists to calculate its density and confirm its rocky nature. This achievement marked a milestone in exoplanet research, offering evidence that rocky planets not only exist outside our solar system, but can also be detected and studied with the technology at our disposal. Building upon the discovery of Kepler 10b, the exploration of this intriguing exoplanet opens doors to deeper questions about the nature of planets beyond our solar system. The methods used to uncover Kepler 10b's secrets, particularly the transit method, where the planet's passage in front of its star leads to a slight dimming of the star's light observed by telescopes, underscore the sophistication of current astronomical techniques. This process not only revealed Kepler 10b's presence, but also provided insights into its composition and physical characteristics, highlighting the potential for further discoveries. Kepler 10b's extreme proximity to its host star raises fascinating questions about its formation and history. How did it end up in such a close orbit? Theories suggest that it might have migrated inward from a more distant orbit over millions of years, a journey that could have dramatically altered its composition and surface features. This scenario prompts a re-evaluation of our understanding of planetary system dynamics and the forces that shape them over time. Furthermore, the study of Kepler 10b has implications for the search for life beyond Earth. While this planet itself is inhospitable to life as we know it, due to its scorching temperatures, its detection demonstrates the capability to find and analyze Earth-sized and potentially habitable planets in other solar systems. This effort is part of a broader quest to identify worlds where conditions might be right for life. Now let's take a step back and explore some of the more familiar planets. Venus, our celestial neighbor, presents a fascinating contrast to Earth, offering a unique perspective on planetary science and the conditions necessary for life. Known as the second planet from the Sun, Venus orbits within our solar system's inner circle, positioned closer to the Sun than Earth. This proximity to our star contributes to Venus's status as the hottest planet in our solar system, with surface temperatures averaging around 465 degrees Celsius, 869 degrees Fahrenheit. Such extreme conditions are primarily due to its dense atmosphere, composed mostly of carbon dioxide, with clouds of sulfuric acid creating a runaway greenhouse effect that traps heat. Despite being similar in size and composition to Earth, earning it the nickname Earth's twin, Venus's surface and atmospheric conditions are vastly different. Its rotation is notably slow, taking about 243 Earth days to complete a single rotation on its axis, which is longer than its orbital period around the Sun of about 225 Earth days. Intriguingly, Venus rotates in the opposite direction to most planets in our solar system, including Earth, meaning the Sun rises in the west and sets in the east on Venus. The exploration of Venus has been a challenging endeavor due to its harsh environment, with numerous missions attempting to study the planet up close. Soviet Venera probes in the 1970s and 1980s provided the first detailed images of its surface, revealing a world covered with volcanic landscapes, vast plains, and high mountain ranges. Recent studies suggest Venus is still geologically active, with potential signs of recent volcanic activity. Venus also exhibits a phenomenon known as ashen light, an apparent faint illumination of its dark side when viewed from Earth, which has been a subject of speculation and study among astronomers for centuries. Additionally, the planet's thick clouds reflect sunlight efficiently, making Venus the third brightest object in the sky visible from Earth, after the Sun and the Moon. Neptune stands as a sentinel in the outer reaches of our solar system, the eighth planet from the Sun and the most distant among the known planets, following the reclassification of Pluto as a dwarf planet. Discovered in 1846, its existence was predicted mathematically before it was visually confirmed, a testament to the power of Newtonian mechanics and a milestone in the history of astronomy. Neptune is 4 times wider than Earth, with a diameter of about 49,244 kilometers, 30,598 miles, making it the smallest of the gas giants in our solar system, yet it packs a dense atmosphere composed primarily of hydrogen and helium, with traces of methane giving it a striking blue hue. Orbiting the Sun at an average distance of 4.5 billion kilometers, about 2.8 billion miles, Neptune takes approximately 165 Earth years to complete a single orbit, which means it has only completed one orbit since its discovery. Despite its distance from the Sun, Neptune's atmosphere is surprisingly active, with dynamic weather systems and the fastest winds in the solar system, reaching speeds of up to 2,100 kilometers per hour, about 1,300 miles per hour. This activity is thought to be driven by the planet's internal heat, rather than solar energy, which is minimal at such a great distance. Neptune's magnetic field is also a subject of interest, as it is tilted significantly relative to its rotation axis and offset from the planet's center, similar to the magnetic field of Uranus. This unusual magnetic orientation may be the result of the planet's internal structure and heat distribution, offering clues about the processes occurring within its deep interior. The planet is encircled by a faint system of rings and 14 known moons, with Triton being the largest and most notable. Triton orbits Neptune in a retrograde direction, meaning it moves in the opposite direction of the planet's rotation, suggesting that it may have been captured by Neptune's gravity and is not a native moon. Triton is geologically active, with cryovolcanoes that eject nitrogen gas and dust particles from beneath its surface, creating a thin atmosphere that, like Neptune's, is mostly nitrogen. The exploration of Neptune has been limited, with the Voyager 2 spacecraft providing the bulk of our current knowledge during its flyby in 1989. The data collected by Voyager 2 revealed Neptune as a world of immense beauty and complexity, with swirling clouds, high-altitude ice crystals, and dark spots indicative of storm systems. These observations have laid the groundwork for future missions that may further unravel the mysteries of this distant planet, deepening our understanding of the outer solar system and the forces that shape it. Uranus, the 7th planet from the Sun, offers a fascinating study in contrasts and surprises within our solar system. Discovered in 1781 by William Herschel, its discovery expanded the known boundaries of our solar system for the first time in modern history. Unlike the more familiar rocky planets of the inner solar system or the gas giants like Jupiter and Saturn, Uranus is often categorized as an ice giant. This classification comes from its unique composition, primarily of water, ammonia, and methane ices, beneath a thick atmosphere of hydrogen and helium. One of the most striking features of Uranus is its dramatic tilt. The planet rotates on its side, with an axial tilt of about 98 degrees, meaning it essentially rolls around the Sun on its orbit. This peculiar orientation leads to extreme seasonal variations, with each pole getting around 42 years of continuous sunlight, followed by 42 years of darkness. This tilt is believed to be the result of a massive collision with an Earth-sized object long ago, which drastically altered the planet's orientation. Uranus is encircled by a complex system of rings, less prominent than Saturn's but equally intriguing. These thin, dark rings were only discovered in 1977, highlighting how much remains to be learned about this distant planet. Additionally, Uranus is accompanied by 27 known moons, each named after characters from the works of William Shakespeare and Alexander Pope, adding a cultural layer to the scientific exploration. Despite its distance and the challenges it presents for observation, Uranus has been visited once by a spacecraft Voyager 2 in 1986. This flyby provided a wealth of data, revealing many of the planet's secrets and leaving many questions unanswered. The pale cyan of Uranus, due to the methane in its atmosphere which absorbs red light and reflects blue, and its calm appearance belie a complex atmospheric system with the fastest winds in the solar system, reaching speeds of up to 900 kilometers per hour. Pluto, once the 9th planet from the Sun in our solar system, has captivated the curiosity and imagination of astronomers and the public alike since its discovery in 1930 by Clyde Tombaugh. Located in the Kuiper Belt, a region filled with icy bodies and remnants from the solar system's formation, Pluto is a dwarf planet, a category that it helped define when the International Astronomical Union, IAU, refined the criteria for planethood in 2006. Despite its reclassification, Pluto continues to be a subject of significant scientific interest and exploration, embodying the mysteries that lie at the edge of our solar system. With a diameter of about 2,377 kilometers, 1,477 miles, Pluto is smaller than Earth's moon. Its orbit is highly elliptical, taking it on a 248 Earth-year journey around the Sun, during which it can come closer to the Sun than Neptune for a period before moving back to its more distant position. This unique orbit contributes to Pluto's complex and variable environment. Pluto's surface is surprisingly diverse, with vast plains, towering mountains, and deep valleys. One of the most striking features is a heart-shaped glacier named Sputnik Planitia, composed of nitrogen ice, which hints at a geologically active world beneath its icy exterior. The presence of mountains made of water ice, which behaves like rock due to the extremely low temperatures, suggests geological processes that have yet to be fully understood. The dwarf planet's atmosphere is thin and composed mostly of nitrogen, with traces of methane and carbon monoxide. As Pluto moves away from the Sun, its atmosphere freezes and falls to the surface as snow, a seasonal change that provides insight into the dynamics of planetary atmospheres under extreme conditions. Pluto's 5 known moons, Charon, Styx, Nix, Kerberos, and Hydra, add another layer of intrigue to its story. Charon, the largest of these moons, is so sizable in relation to Pluto that they are often considered a double dwarf planet system. The gravitational dance between Pluto and Charon presents a fascinating dynamic, with both bodies orbiting a point in space between them, rather than Pluto being the sole center of orbit. The exploration of Pluto, particularly by the New Horizons spacecraft in 2015, has opened a new chapter in our understanding of the outer solar system. New Horizons flyby provided unprecedented detail about Pluto's surface, atmosphere, and moons, shedding light on a world that is far more complex and dynamic than previously imagined. Jupiter's moon Io stands as a celestial body of extreme contrasts and profound fascination within our solar system. Discovered in 1610 by Galileo Galilei alongside 3 other moons orbiting Jupiter, Io marks itself as the innermost of the Galilean moons and is heralded for its dramatic geological activity. This moon, slightly larger than Earth's own moon, is characterized by over 400 active volcanoes on its surface, making it the most volcanically active body in our solar system. The source of this intense volcanic activity lies in the powerful gravitational tug-of-war between Jupiter and the other Galilean moons, Europa and Ganymede, which causes immense tidal heating within Io's interior, flexing and heating its interior to keep its mantle and core in a molten state. Io's surface is a tapestry of sulfur and sulfur dioxide frost, giving it a colorful appearance with yellow, red, white, black, and green hues, unlike any other celestial body we know. This vivid landscape is constantly being reshaped by volcanic eruptions that can eject plumes of material up to 500 kilometers, about 310 miles, into space, creating extensive basins and depositing large amounts of sulfur in various forms. Despite its hostile environment, Io plays a crucial role in our understanding of geological processes beyond Earth. It challenges scientists to reconsider notions of planetary and moon formation, the conditions necessary for volcanic activity, and the potential for life in extreme environments. The study of Io has also provided insights into the magnetic and gravitational interactions within the Jupiter system, particularly how Io contributes to Jupiter's magnetic environment by generating an electric current known as the Io flux tube, which produces intense auroras on Jupiter. The exploration of Io has been primarily through flyby missions, most notably by the Voyager spacecraft in the late 1970s and the Galileo orbiter in the 1990s and early 2000s. These missions have offered glimpses into Io's complex and dynamic environment, revealing a world where the ground is literally never still. Continuing our exploration of Io, Jupiter's fascinating moon, we delve deeper into the implications of its unique geologic and volcanic features. The immense volcanic activity on Io is not just a spectacle of nature's power, but also a window into the internal dynamics of celestial bodies. The heat generated by tidal forces within Io's interior leads to frequent and massive volcanic eruptions, shaping a landscape that is constantly being renewed and reformed. This process offers scientists a live laboratory to study how volcanic activity can affect a body's surface, atmosphere, and even its potential habitability. One of the most striking discoveries about Io is the presence of lava lakes and vast flows of molten rock that cover large swathes of its surface. These features indicate that Io's mantle must be incredibly hot, with some estimates suggesting temperatures exceeding 1,200 degrees Celsius, about 2,192 degrees Fahrenheit, in certain areas. The composition of these lavas, rich in silicates and sulfur compounds, differs from the typical basaltic flows found on Earth, providing clues about the moon's formation and the elemental makeup of the outer solar system. Io's influence extends beyond its own orbit, impacting Jupiter's magnetosphere. The moon ejects about 1 ton of material into space every second through its volcanic plumes, contributing to a torus of plasma that encircles Jupiter. This interaction not only fuels Jupiter's auroras, but also creates a complex electromagnetic environment that challenges our understanding of planetary magnetospheres. The study of Io has broader implications for the search for life beyond Earth. While Io itself is too hostile for life as we know it, its volcanic activity underscores the diverse conditions under which moons and planets can exist. Understanding Io helps refine our models of celestial dynamics and habitability, informing the search for life-supporting environments in other star systems. Future missions to the Jupiter system, such as the European Space Agency's Jupiter Icy Moons Explorer, scheduled for launch in the 2020s, and NASA's Europa Clipper, aim to further explore Io and its fellow Galilean moons. These missions will provide new insights into Io's volcanic activity, its interaction with Jupiter's magnetic field, and the moon's role in the larger Jovian system. Io remains a symbol of the dynamic and active processes that can exist on moons throughout the universe, challenging our perceptions of where and how dynamic geological activity can occur. Its study enriches our understanding of the solar system, offering lessons on the forces that shape celestial bodies and the potential for discovering even more worlds of wonder beyond our own. Saturn's moon Titan stands as one of the most intriguing and distinctive bodies in our solar system, capturing the fascination of scientists and space enthusiasts alike. As the largest moon of Saturn and the second largest in the solar system, Titan is unique in having a dense atmosphere, thicker than that of Earth, composed mainly of nitrogen with traces of methane and hydrogen. This thick atmosphere obscures the moon's surface from view in visible light, requiring radar and infrared instruments to peer through the haze. What sets Titan apart from all other moons in our solar system is its complex weather system, including rain, rivers, lakes, and seas, though not of water, but of liquid methane and ethane. This discovery has led to Titan being one of the most Earth-like worlds we know of, albeit with a frigid surface temperature averaging around -179 degrees Celsius, -290 degrees Fahrenheit. Despite these chilly conditions, Titan's atmosphere and surface processes mirror those of Earth's own hydrological cycle, with evaporation, cloud formation, and precipitation shaping the landscape. Titan's surface is varied and includes vast dunes of hydrocarbon sands, mountain ranges, and a multitude of liquid hydrocarbon lakes in the polar regions, making it an object of intense scientific study. The presence of liquid bodies on Titan makes it a prime candidate in the search for extraterrestrial life, particularly in exploring the prebiotic chemistry that could lead to life. The Cassini-Huygens mission, a collaboration between NASA, ESA, European Space Agency, and ASI, Italian Space Agency, has been instrumental in unveiling Titan's secrets. When the Huygens probe descended onto Titan's surface in 2005, it provided humanity's first close-up view of this alien landscape, revealing a complex world with features reminiscent of Earth, such as river channels and stones smoothed by liquid erosion. This exploration of Titan has opened up new questions about the moon's past and present, including the sources of its methane, the mechanisms driving its climate and geological processes, and the potential for hosting simple forms of life in its vast liquid reservoirs. Delving deeper into the mysteries of Titan, Saturn's largest moon, we find a world that continues to captivate with its potential for scientific discovery. Beyond its Earth-like weather systems and hydrocarbon lakes, Titan holds clues to the solar system's history and the complex chemistry that could lead to life. One of the most intriguing aspects of Titan is its subsurface ocean, believed to lie beneath the icy crust. This hidden ocean, possibly composed of water mixed with salts and ammonia, represents a key interest for astrobiologists searching for extraterrestrial life. The interaction between the liquid water ocean and the rocky mantle beneath could create conditions suitable for chemical reactions foundational to life as we know it. The study of Titan is not just about understanding another world in our solar system. It's also about gaining insights into Earth's past and the potential for life elsewhere in the universe. Titan's thick atmosphere, rich in organic molecules, acts as a window into the chemical processes that might occur on exoplanets with similar conditions. The complex organic chemistry occurring in Titan's atmosphere and on its surface, driven by sunlight and possibly by cryovolcanism, creates a vast array of compounds that could be precursors to more complex molecules associated with life. Future missions to Titan, such as NASA's Dragonfly mission slated for launch in the 2030s, aim to explore its chemistry and habitability further. Dragonfly is a drone-like rotorcraft designed to fly through Titan's dense atmosphere, covering much greater distances than a traditional lander or rover could. Its goals include studying prebiotic chemistry and habitability at various locations, analyzing the moon's surface and subsurface properties, and investigating its atmospheric and surface processes. By directly sampling Titan's environment and conducting detailed analyses, Dragonfly seeks to unlock the secrets of this enigmatic moon, potentially reshaping our understanding of life's origins and existence beyond Earth. UMHUA, a fascinating object that captured the world's attention when it was discovered on October 19, 2017, by astronomers using the Pan-STARRS 1 telescope in Hawaii. Its name, UMHUA, comes from the Hawaiian term for scout, or messenger from afar arriving first, reflecting its status as the first known interstellar object to pass through our solar system. What sets UMHUA apart from other celestial bodies observed by scientists is its highly elongated shape. Unlike any comet or asteroid seen in our solar system, and its surprising acceleration as it traveled away from the Sun, behavior not typically expected from a natural celestial object without any visible signs of outgassing or a tail. Measuring roughly 800 meters long and only about 80 meters wide, UMHUA's cigar-like shape is unprecedented. Observations and analyses suggest it is a dark red color, indicative of a surface rich in organic molecules that may have been irradiated by cosmic rays for millions, if not billions, of years. Its exact origin remains a mystery, but it's believed to have been ejected from another stellar system before making its solitary journey through the cosmos and eventually passing by Earth. The trajectory and speed of UMHUA, combined with its non-gravitational acceleration as it moved away from the Sun, sparked intense debate and speculation among astronomers. Some theories suggest that its acceleration could be attributed to outgassing, a process common in comets where ice turns into gas and drives the comet forward. However, the lack of a visible comet-like tail or coma around UMHUA challenged this explanation, leading to a variety of alternative theories, including the less conventional suggestion that UMHUA might be an artificial object. The intrigue surrounding UMHUA deepened as further analysis of its properties and behavior continued to challenge conventional understanding of comets and asteroids. One of the most perplexing aspects of UMHUA was its rotation. Observations indicated that it was tumbling rather than smoothly rotating, and its brightness varied dramatically, suggesting that it was highly elongated and possibly flat rather than cigar-shaped as initially thought. This unusual rotation and shape hinted at a violent past, perhaps involving a collision that sent it hurtling out of its original stellar system and into interstellar space. Another point of intense debate among scientists is the origin of UMHUA. While it's clear that it came from outside our solar system, pinpointing its exact home has proven to be challenging. Some theories propose that UMHUA could be a fragment from a larger object that was torn apart during a close encounter with a star or planet, while others suggest it might be a remnant of a planetary building block that never formed into a full-fledged planet. The diversity of theories reflects the limited data available and the novelty of studying such an object, underscoring the need for continued observation and research on interstellar visitors. UMHUA's brief visit also highlighted the limitations and capabilities of current astronomical technologies and the importance of being prepared for future encounters with interstellar objects. Since its departure, there has been a concerted effort within the scientific community to enhance observation techniques and develop strategies for rapidly responding to similar phenomena. This includes proposals for missions that could intercept or rendezvous with incoming interstellar objects, providing unprecedented opportunities for in-situ study and potentially answering long-standing questions about the composition and nature of material from other star systems. In reflecting on the UMHUA encounter, it's clear that this mysterious visitor has had a lasting impact on astronomy and our understanding of the cosmos. It has sparked conversations about the need for international cooperation in monitoring the skies for future interstellar objects and the potential for groundbreaking discoveries that such objects hold. As technology advances and our ability to detect and study these visitors from afar improves, we stand on the brink of a new frontier in our quest to understand the universe and our place within it. Eris, nestled far beyond the familiar planets of our solar system, invites intrigue and mystery as one of the most distant known dwarf planets. Discovered in 2005, Eris significantly contributed to the redefinition of what constitutes a planet, leading to the demotion of Pluto to the status of a dwarf planet. Located in the scattered disk, a remote area of the solar system, Eris orbits the Sun at a distance so vast that it completes a single orbit approximately every 558 years. This celestial body is named after the Greek goddess of discord and strife, a fitting title considering the astronomical debate its discovery sparked. Eris measures about 2,326 kilometers in diameter, making it slightly smaller than Pluto, but remarkably dense, suggesting it is primarily composed of rock and ice. This composition hints at the conditions and materials present in the outer solar system during its formation. One of the most fascinating aspects of Eris is its surface, which is exceptionally reflective, suggesting it is covered in a thin layer of frozen methane. Observations indicate that Eris's surface undergoes changes in brightness as it moves away from the Sun, which could be due to the sublimation of surface ice into gas, altering its reflectivity. Eris has one known moon, Dysnomia, named after the daughter of the Greek goddess Eris, representing lawlessness. The discovery of Dysnomia played a crucial role in determining Eris's mass, which is found to be approximately 27% greater than that of Pluto. This measurement was instrumental in understanding more about the dwarf planet's characteristics, including its density and composition. The story of Eris is not just about a distant dwarf planet. It is a narrative that reshaped our understanding of the solar system. Its discovery prompted the International Astronomical Union to redefine the criteria for planethood in 2006, which now requires a celestial body to orbit the Sun, be spherical in shape, and have cleared its orbit of other debris. Eris's presence in the Kuiper Belt, a region teeming with icy bodies, challenged the notion of what it means to dominate an orbit, contributing to the creation of the dwarf planet category. Diving deeper into the exploration of Eris, we delve into the scientific endeavors and future prospects surrounding this distant world. The intrigue surrounding Eris extends beyond its pivotal role in the reclassification of Pluto. It represents a frontier of discovery in the outer reaches of our solar system, where the conditions are starkly different from those of the inner planets. One of the most compelling aspects of Eris is its atmosphere. Observations suggest that Eris possesses a tenuous atmosphere of nitrogen and methane, similar to that of Pluto. This atmosphere is thought to expand when Eris approaches closer to the Sun along its elliptical orbit and frees onto the surface as it moves away. This dynamic process offers valuable insights into atmospheric physics in extremely cold environments, far from the warmth of the Sun. Eris's orbit, taking it as far as 97 astronomical units, AU, from the Sun, 1 AU is the average distance from the Earth to the Sun, places it in a region of space that is difficult to study. Despite the challenges, the New Horizons mission to Pluto and the Kuiper Belt has sparked interest in missions that could explore Eris and other distant objects. Such a mission would not only shed light on Eris itself, but also on the nature of the scattered disk, a less understood region of the solar system that is home to many other icy bodies. The study of Eris and its comparison with other dwarf planets like Pluto and Haumea is crucial for understanding the diversity of objects in our solar system. Each of these bodies has unique characteristics, from their geological features to their atmospheres and moons, offering clues about the processes that dominate in these distant reaches. For instance, the similarities and differences between the atmospheres of Eris and Pluto can help scientists understand how atmospheric conditions evolve in response to their orbits and distances from the Sun. Looking to the future, Eris holds the potential to answer key questions about the solar system's formation and evolution. Its composition, particularly the ratio of rock to ice, can provide insights into the materials present in the outer solar system during its early history. Additionally, studying Eris's surface features, such as craters and possible cryovolcanoes, could reveal the impact, history, and internal processes of this remote dwarf planet. Advancements in telescope technology and the possibility of dedicated missions to the Kuiper Belt and beyond mean that our understanding of Eris is poised to grow. The James Webb Space Telescope, with its unprecedented sensitivity and resolution, is expected to offer new views of Eris, potentially uncovering features that have remained elusive. Sedna, an enigmatic object within our solar system, offers a fascinating glimpse into the vast and largely unexplored region beyond Neptune. Discovered in 2003, Sedna's orbit is one of the most distant and eccentric, taking it from about 76 astronomical units, AU, at its closest approach to the Sun, to an astonishing 936 AU at its farthest, a journey that takes approximately 11,400 Earth years to complete. This extraordinary orbit challenges our understanding of the solar system's formation and the forces shaping its outer boundaries. With a diameter estimated to be about 1,000 kilometers, Sedna is smaller than Pluto, classifying it as a dwarf planet, though it has yet to be officially designated as such by the International Astronomical Union. Its surface is one of the reddest in the solar system, suggesting the presence of organic molecules or tholins, which are complex compounds that form when ultraviolet sunlight irradiates simple organic compounds such as methane and ethane. The discovery of Sedna was significant because it resides in a region of space that was previously believed to be largely empty. Its presence, along with that of other distant objects discovered since, suggests the existence of a vast and previously unknown population of similar bodies in the outer solar system, sometimes referred to as the inner Oort cloud, or sednoids. These objects could be remnants from the early solar system, providing critical clues about its formation and the distribution of small bodies beyond Neptune. One of the most intriguing aspects of Sedna's discovery is the insight it offers into the gravitational influences at the edge of our solar system. The peculiar orbit of Sedna, which does not bring it close enough to be significantly affected by Neptune or the other giant planets, suggests that either it was perturbed by a yet undiscovered massive object far beyond Neptune, or it was captured from another star during the Sun's early history in a dense star cluster. One of the most tantalizing theories that Sedna's discovery has fueled is the possibility of a yet undiscovered ninth planet, sometimes referred to as Planet 9. This hypothetical planet is theorized to be influencing the orbits of Sedna and other distant objects through its gravitational pull. If it exists, Planet 9 could be several times the mass of Earth, lurking unseen in the dark regions far beyond Neptune. The search for this elusive planet involves complex simulations and observations, aiming to explain the anomalies in the orbits of Sedna and similar objects. Sedna's long journey around the Sun also offers a unique opportunity to study the Sun's influence over vast distances. As Sedna moves closer to the Sun in its eccentric orbit, it could potentially develop a very faint coma or atmosphere, much like comets do when they approach the Sun. Observing these phenomena could provide insights into the composition of Sedna and the mechanisms by which bodies in the solar system interact with solar radiation and the solar wind, even at extreme distances. Moreover, Sedna's existence challenges and refines our models of the solar system's early dynamics. It supports the hypothesis that the Sun was once part of a dense star cluster where close encounters with other stars could have dramatically affected the orbits of the outer solar system's objects. Alternatively, Sedna's peculiar orbit could be the result of interactions with unseen celestial bodies or even a passing star, suggesting a more chaotic early solar system than previously thought. The exploration of Sedna and the quest to understand its origins and properties highlight the dynamic and ever-evolving nature of our solar system. Each discovery brings with it new puzzles and propels our scientific capabilities and curiosities further into the cosmos. Future missions, possibly involving flybys or even orbiters, could one day unravel the mysteries of Sedna. Kepler 1625 b is an exoplanet that has captured the attention of astronomers and the public alike due to its intriguing characteristics and the possibility that it hosts a moon, akin to a giant version of our own Earth-Moon system. Discovered by the Kepler space telescope, which was launched by NASA to search for Earth-like planets orbiting other stars, Kepler 1625 b resides in the constellation Cygnus, approximately 4,000 light-years from Earth. The planet orbits its host star, Kepler 1625, a star similar to our Sun but larger and older, every 287 days, a period that places it in or near the habitable zone of its star, where liquid water could potentially exist. Kepler 1625 b is a gas giant, several times the size of Jupiter, making it a type of planet known as a hot Jupiter, although its specific conditions and temperature depend heavily on its atmosphere and distance from its star. The most striking aspect of Kepler 1625 b's discovery was the potential detection of a moon orbiting the planet, which would be the first moon outside our solar system ever identified, colloquially known as an exomoon. This possible exomoon, unofficially named Kepler 1625 Bi, is estimated to be the size of Neptune, making it an unprecedented find, as moons of this size are not found in our solar system, and it challenges existing theories of moon formation. The detection of the exomoon is based on transit observations, where the planet and its moon pass in front of their host star, causing a temporary dimming of the star's light that can be measured from Earth. The data suggests that the moon's gravitational pull influences Kepler 1625 B's orbit around its star, leading to variations in the timing and duration of the transits. These observations have sparked considerable interest and debate in the scientific community, with further analysis and additional observations needed to confirm the existence of the moon and understand its characteristics. The intrigue surrounding Kepler 1625 B and its potential exomoon extends into the realm of what these celestial bodies can teach us about the cosmos. The study of such an unusual moon, especially one that rivals Neptune in size, could revolutionize our understanding of moon formation theories and the dynamics of planetary systems far beyond our own. The very notion that moons could be as large as planets introduces a fascinating complexity into the architecture of solar systems, suggesting a diversity in celestial formations that was previously unimagined. Further investigations into Kepler 1625 B and its potential exomoon are crucial for astronomers seeking to unravel the mysteries of exoplanetary systems. Observations and models suggest that the formation of such a large moon might involve processes distinct from those that gave rise to the moons in our solar system. For instance, it could have formed from a disk of gas and dust surrounding Kepler 1625 B in its early stages, or it might even be a captured rogue planet ensnared by Kepler 1625 B's gravitational pull. The presence of this exomoon could also have significant implications for the environment of Kepler 1625 B itself. If confirmed, it would provide a rare opportunity to study the interactions between a planet and its moon in a system very different from our own. For example, the gravitational forces between the planet and the moon could affect their rotational dynamics, leading to tidal heating, which might influence the internal geology and atmospheric conditions of the moon. Moreover, the potential habitability of such an exomoon sparks curiosity and speculation. While Kepler 1625 B, a gas giant, is unlikely to be habitable, its moon, if it has a rocky composition and an atmosphere, could present conditions conducive to life, at least theoretically. The prospect of an exomoon with an environment that could support life adds an exciting dimension to the search for extraterrestrial life, expanding the focus from planets to their moons. The quest to confirm the existence of the exomoon and understand its nature involves sophisticated observational techniques and future space missions. Telescopes such as the Hubble Space Telescope and the upcoming James Webb Space Telescope play pivotal roles in this endeavor, offering the high-resolution imaging and spectroscopy needed to detect and characterize distant exoplanets and their moons. These observations, combined with advanced computer modeling, will help scientists piece together the story of Kepler 1625 B and its companion, shedding light on the formation and evolution of complex planetary systems. Kelt 11b is a fascinating exoplanet discovered by astronomers using the Kilodegree Extremely Little Telescope survey, which specializes in finding exoplanets around bright stars. Located approximately 320 light-years away from Earth in the constellation Sextans, Kelt 11b orbits the star Kelt 11, a bright, evolved star that is nearing the end of its life cycle. This proximity to its host star provides a unique opportunity for scientists to study the exoplanet's atmospheric composition in detail. Kelt 11b is classified as a hot Jupiter, a type of gas giant exoplanet that is similar in characteristics to Jupiter but orbits very close to its star, resulting in much higher surface temperatures. However, Kelt 11b stands out among hot Jupiters due to its extremely low density. It is one of the least dense exoplanets ever discovered, with a density so low that it is nearly as inflatable as a balloon. This low density suggests that the planet has a very extended atmosphere, making it an excellent target for atmospheric studies. The planet's close orbit around its host star, completing a full revolution in just under 5 days, subjects it to intense stellar radiation. This proximity not only contributes to its high temperature, but also likely affects its atmospheric dynamics, potentially leading to atmospheric escape, where the outer layers of the atmosphere are blown away by stellar wind and radiation. Kelt 11b's large radius, nearly 40% larger than Jupiter's despite its lower mass, and its extended atmosphere provide a rare opportunity to analyze the chemical makeup of an exoplanet's atmosphere. The atmosphere's extended nature allows for the detection of various molecules through the process of transmission spectroscopy, where scientists observe the starlight that passes through the planet's atmosphere during transits. This method can reveal the presence of water vapor, carbon monoxide, and other important compounds, offering insights into the planet's formation and evolution. The intrigue surrounding Kelt 11b extends into the implications of its findings for the broader field of exoplanet research. The exceptional characteristics of Kelt 11b, particularly its low density and extended atmosphere, serve as a paradigm for understanding the physics and chemistry of hot Jupiters. These insights are pivotal in piecing together the evolutionary puzzle of gas giants under intense stellar irradiation, offering clues about their atmospheric retention, heat distribution, and potential for atmospheric escape over time. One of the most compelling aspects of studying Kelt 11b is what it can teach us about the life cycle of planetary atmospheres. The extended atmosphere of Kelt 11b, exposed to extreme conditions, may undergo processes that are not observed in the atmospheres of more dense and compact planets. For instance, the phenomenon of atmospheric escape, where lighter molecules are stripped away from the planet by the star's radiation, is likely occurring at a significant rate on Kelt 11b. Understanding this process gives scientists valuable insights into how planets lose their atmospheres and the timescales over which this transformation can happen, which has implications for the habitability of planets over their lifetimes. The study of Kelt 11b's atmosphere through transmission spectroscopy opens a window into the chemical and thermal structures of hot Jupiter atmospheres. The detection of specific molecules, their distribution, and how they interact with incoming stellar radiation can inform models of atmospheric dynamics and chemistry. These models, in turn, help scientists predict the conditions on similar planets yet to be observed in detail, broadening our understanding of planetary atmospheres across the galaxy. The research into Kelt 11b and its atmospheric properties also underscores the importance of future telescopic missions and the development of new observational technologies. Instruments, such as the James Webb Space Telescope and the upcoming extremely large telescopes on the ground, are poised to provide even more detailed observations of Kelt 11b and other exoplanets. These advanced tools will enable the detection of fainter signals and the identification of more complex molecules in exoplanet atmospheres, further enriching our understanding of their composition and behavior. The HR 8799 system is an extraordinary and pioneering discovery in the field of astronomy, offering a fascinating glimpse into a planetary system that mirrors a young version of our own solar system. Located about 129 light-years away in the constellation Pegasus, this system is centered around HR 8799, a young main-sequence star that is slightly more massive and brighter than our Sun. The HR 8799 system is particularly renowned for being one of the first where multiple exoplanets were directly imaged, marking a significant milestone in the study of planetary systems beyond our own. Discovered incrementally between 2008 and 2010, the HR 8799 system consists of 4 massive exoplanets, known as HR 8799 E, D, C, and B, moving in orbits far from their parent star. These planets are gas giants, with masses ranging from about 7 to 10 times that of Jupiter, making them some of the largest exoplanets discovered to date. Their orbits range from relatively close to the star to more extended orbits, with the outermost planet, HR 8799 B, orbiting at a distance comparable to Pluto's orbit in our solar system. One of the most striking features of the HR 8799 system is the direct imaging of its planets. Unlike the majority of exoplanets detected through indirect methods like the transit or radial velocity techniques, the planets of HR 8799 were observed directly using powerful telescopes equipped with adaptive optics systems. These systems correct the blurring effect of the Earth's atmosphere, allowing for clearer images of celestial objects. The direct imaging of these exoplanets has provided astronomers with invaluable data regarding their atmospheres, compositions, and orbital dynamics. The planets of the HR 8799 system are young, with estimated ages of around 30 million years. This youthfulness means they are still glowing with residual heat from their formation, making them easier to observe with infrared telescopes. Observations have revealed that these planets have complex atmospheres with clouds and possibly even weather systems, similar to what is found in the gas giants of our solar system. Moreover, the HR 8799 system is surrounded by a vast debris disk, composed of dust and ice, which is thought to be the remnants of the process that formed the planets, and possibly hints at the presence of additional smaller bodies within the system. Continuing the exploration of the HR 8799 system, we delve deeper into the scientific significance and the future prospects of studying such a uniquely detailed planetary system. The HR 8799 system's direct imaging provides an unprecedented opportunity to study the atmospheric composition, orbital mechanics, and even the climate of exoplanets in great detail, offering a wealth of information about how planetary systems develop and evolve over time. The atmospheres of the HR 8799 planets are of particular interest to astronomers. Spectroscopic analysis, which examines the spectrum of light emitted or absorbed by the planets, can reveal the presence of various gases and potentially provide clues about atmospheric dynamics and weather patterns. For instance, the detection of water vapor, methane, and carbon monoxide in these planets' atmospheres would not only confirm theories about the chemical makeup of gas giants, but also offer insights into the processes that dominate their weather and climate systems. The HR 8799 system's debris disk plays a crucial role in understanding the formation and evolution of planetary systems. By studying the distribution and composition of the debris disk, scientists can infer the presence of other, smaller bodies within the system, such as asteroids or comets, which may impact the development of the system's planets. The disk also provides clues about the late stages of planetary formation, offering a glimpse into the processes that may have occurred in the early solar system. The future study of the HR 8799 system will benefit significantly from advancements in telescope technology and observation techniques. Projects like the James Webb Space Telescope, JWST, and ground-based telescopes equipped with next-generation adaptive optics will be able to capture even more detailed images and spectra of the HR 8799 planets. These observations will enhance our understanding of the planet's atmospheres, including their compositions, temperature profiles, and potential weather phenomena. The study of the HR 8799 system has implications for the search for life beyond Earth. While the gas giants themselves are unlikely to host life as we know it, their detailed study can inform our understanding of the habitability of other planetary systems. By learning how gas giants and their moons form and evolve, scientists can better assess the potential for habitable environments elsewhere in the galaxy. As we near the end of this documentary, we are reminded that the universe is filled with mysteries waiting to be unraveled and wonders yet to be discovered. The quest to understand the cosmos and our place within it has never been more alive. With each passing day, new technologies and methodologies are being developed, opening up new possibilities for discovery and exploration. What lies beyond the next horizon? Only time and our relentless pursuit of the unknown will tell. But one thing is certain, the journey is far from over, and the best discoveries are yet to come. Thanks for watching.